subspaces. A vector space is a mathematical structure formed by a collection of elements called vectors, which may be added together or multiplied by a number called scalar. For the concept of a vector space, we start immediately with the most important spaces. They are denoted by R1, R2, R3, and so on. The space Rn consists of all column vectors with n components. So R represents the set of real numbers. All the components are set of real numbers. R1 will be one-dimensional space, which is a line. R2 represents xy plane. The two components of the vector become the x and y coordinates of the corresponding points. R3, three-dimensional space, gives three components of a vector. A real vector space is a set of vectors together with rules for vector addition and multiplication by real numbers. Addition and multiplication must produce vector in the space, and they must satisfy the 8 conditions. So before defining the vector space, first let me define fields. What is a field? So a field is nothing but a set F which contains at least two elements on which two operations plus and dot, that is addition and multiplication, are defined, so that for each pair xy in F there are unique elements x plus y and x dot y or xy in F satisfying the following axioms for all elements in xyz in F. So what is a field? Field is nothing but a set F, so which containing at least two elements on which two operations plus and dot are defined, so that for each pair in x and y, x plus y and x dot y are in F. So which satisfying the following axioms. So for all elements x, y, z in F, let us consider the following axioms as like the commutative, associative, identity, existence of inverse with respect to addition, and also the multiplication. X plus y is equal to y plus x, called the commutative addition. X plus y plus z is equal to x plus y plus z, associative of addition. So there is an element 0 belongs to F called 0, such that x plus 0 is equal to x is nothing but the existence of an additive identity. So for each x there is an element minus x belongs to F, such that x plus minus x is equal to 0, that is existence of inverse. Similarly, we have the axioms with respect to multiplication: commutative, associative, distributive, identity, and inverse. So for each element x, y, z in F which satisfies these axioms, then we say that F is a field. So with this definition of field, let me define a vector space. Let V be a non-empty set with the two operations like the vector addition and scalar multiplication. So vector addition, it will be like for any two elements in V, a sum u plus v in V. For any scalar in F and an element in U, the product cu in F. So with respect to these operations, V is called a vector space over the field F if the following axioms holds for any vector u, v, w belongs to V. So let us have the axioms as similar to the field. So here we have to verify the same axioms with respect to addition and multiplication. Number one is associative. U plus v plus w is equal to u plus v plus w. Then identity, axiom, inverse axiom, commutative axiom with respect to addition, then scalar multiplication with respect to addition, then distributive law, and then again scalar multiplication. AB times U is equal to A into BU for any scalars AB belongs to A. 1 into U is equal to U for any unit scalar where 1 belongs to F. So with respect to addition and scalar multiplication, if the elements of V satisfies the following axioms, then we say that V is a vector space over the field F. Let me have few examples of the vector space. Number one is n-tuple space Rn. Let F be a field and n be a positive integer. Let Fn be the set of all ordered n tuples of the elements of the field F. That is how this Fn will be. So it contains n tuples where each element belongs to F. x1 to xn such that xi belongs to F. So to verify Fn is a vector space, we have to consider the vector addition and the scalar multiplication. So let me take two elements in Fn, which is in the form alpha is equal to x1, x2 and so on xn, and beta is equal to y1, y2 and so on yn. So Fn is a vector space over F if the following axioms are satisfied. Just we have to verify the axioms which we have discussed in the definition. If any elements belongs to V satisfies these axioms, then V is a vector space. So let us verify Fn is a vector space. Let us consider the vector addition. x1 comma x2 and so on xn plus y1 comma y2 and so on yn. So component wise addition, x1 plus y1 plus x2 plus y2. So as we know the vector addition in the usual way, in the similar way, adding the elements component wise. So we get the vector in the form x1 plus y1, x2 plus y2 and so on xn plus yn, which belongs to Fn. Then scalar multiplication, let C belongs to F and x1 x2 belongs to Fn. Then multiplying C component wise, we get C into x1, C into x2 and so on C into xn. So therefore this again belongs to Fn. So 0 vector in Fn is the n tuples of 0 in the form 0, 0, 0. Negative vector is defined as minus of x1, x2 and so on xn. So taking minus sign inside, minus x1, minus x2 and so on minus n, which is again is Fn, which belongs to Fn. So just we can verify few axioms. That is, if vector addition and scalar multiplication is satisfied, then we say that V is a vector space. Here there will be an existence of identity element and the inverse, so therefore V is a vector space. Let me take one more example, the matrix space. That is, if V is a vector space which contains the set of all matrices of order n cross n over set of real numbers. So with matrix addition and the operation of scalar multiplication by real numbers is a vector space. So let us show the matrix addition and the scalar multiplication. So here I will consider a matrix of order 2 cross 2, and I will take two elements in V. Let U is equal to A11, A12, A21, A22, and V is equal to B11, B12, B21, B22. Let us find the vector addition. So as we know, according to algebra of matrices, so sum of two matrices is again a matrix. So U plus V belongs to V, obviously. So making the sum component wise, again we get a 2 cross 2 matrix which belongs to V. And let us find the scalar multiplication. Let C belongs to F and U belongs to V. Then CU is equal to C times the matrix U. So C will be multiplied to each element of the matrix according to the property of matrices. So therefore, Cu is again a matrix of order 2 cross 2 which belongs to V. So therefore, V is equal to set of M of order n cross n of all matrices over R is a vector space with respect to addition and scalar multiplication. So this is how we can show the matrix of order m cross n is a vector space. We also have given some more examples. You can go through it. The next very important thing is a subspace. After the vector space, so we'll have a subspace. What is a subspace? So a non-empty subset W of a vector space V over a field F is called a subspace of V. So easily you can understand a non-empty subset. The subspace is denoted by W, vector space is denoted by capital V. Okay. So a non-empty subset W of a vector space V over a field F is called a subspace of V. If W itself is a vector space over F under the same operations of addition and scalar multiplications defined in V. This is clear. So what is a subspace? A non-empty subset. A non-empty subset W of a vector space over a field F is called a subspace of V if W itself is a vector space under the same operations of addition and scalar multiplication. So in example, here I have given two important subspaces, that is the set 0 consisting of 0 vectors of V, the whole vector space of V. So with this definition of a subspace, let me have an important theorem which gives a useful criteria for a subset W of a vector space to be a subspace. What this theorem says: a non-empty subset W of a vector space V over a field F is a subspace of V if and only if, number 1, for every alpha beta belongs to W, alpha plus beta belongs to W. Number 2, for every C belongs to F, alpha belongs to W, gives C alpha belongs to W. So what we mean by this theorem? So this is a very useful criteria for a subset W of a vector space. So in order to verify W is a subspace, it is enough to prove this theorem. It is enough to verify the conditions 1 and 2. Okay, so the number 1 condition is nothing but the W is closed under addition, and the second condition we call the scalar multiplication. So this is the closure now, right? So it is closed under addition and it is closed under multiplication. So if for every alpha beta belongs to W, for any two vectors in W, then alpha plus beta belongs to W. For every C belongs to F and alpha belongs to W, C alpha belongs to W. So in order to have a subspace of W, subspace of a vector space V, then W will be closed under addition and scalar multiplication. Easily we can prove this theorem. So let me have a corollary to this theorem. A non-empty subset W is a subspace of a vector space V over F if and only if C1 alpha plus C2 beta belongs to W. For every alpha belongs to W, C1 C2 belongs to F. So we can use this corollary to verify W is a subspace. Just we have to show C1 alpha plus C2 beta belongs to W for every two scalar C1 C2 in F and for every vector alpha beta belongs to W. So this theorem and this corollary are very important to verify W is a subspace. Let me consider a few examples on the vector space and the subspace. Number 1. Let P is equal to R3. What do you mean by R3? The vector space of all ordered triplets of real numbers over the field of real numbers show that the subset W is equal to x00 such that x belongs to R is a subspace of R3. So we have a vector space all ordered triplets. We have to verify the given subset W in the form set of all x comma 0 comma 0. So this set contains the elements in the form x comma 0 0 such that all x are real numbers. We have to show that this is a subspace of R3. Show that the subset W is a subspace of R3. So as we know, according to the definition and the theorem and the corollary which we have discussed above, so it is enough to verify W is closed under addition and scalar multiplication. If you verify it is closed under addition and scalar multiplication, then W is a subspace of R3. So let us first verify whether W is a empty or non-empty set. The element 0 in the form 0 0 belongs to W. The 0 is a real number, so thus we can say W is a non-empty set. So let me consider two elements of W. Let it be denoted by alpha 1, which is in the form x1 0 0, and another element alpha 2 in the same form x2 0 0. And what I am doing here, I am showing W is a subspace. So for that I am considering two elements or the vectors, okay, of W in the form alpha 1 and alpha 2. Then let us have the vector addition. Alpha 1 plus alpha 2 gives x1 0 0 plus x2 0 0. Component wise addition, as we know how to add the vectors. x1 plus x2 plus 0 plus 0 plus 0 plus 0, which is again in the same form. Therefore we can say this element will be in W. So if this belongs to W, then addition will be in W. So alpha 1 plus alpha 2 belongs to W. Therefore W is closed under addition. For any scalar, C belongs to R, C into alpha 1. C into alpha 1 is equal to C into x1 0 0. Multiplying, taking the C inside, it will multiply to each element, gives C into x1 0 0, which belongs to W. So therefore W verifies the two conditions of the subspace. So hence we can say W is closed under addition and the scalar multiplication. Hence W is a subspace of R3. Subspace of R3. So it is easy to verify. Let me take one more example. So in this example, show that the set of non-singular 2 by 2 matrices is not a vector space. Show also that the set of singular 2 by 2 matrices is not a vector space. First let us show that the set of non-singular matrices is not a vector space. So let us consider two non-singular matrices. A is in the form 0 0 0 and B is 0 0 0. What are the determinants? 0, hence they are non-singular, right? What will be their sum? Their sum is 1 0 0 0 plus 0 0 0 1. So adding the entries component wise gives 1 0 0 1 an identity. So sum is an identity, but identity matrix is a singular matrix. So therefore the sum of two non-singular is a singular matrix. Hence not closed under addition. So therefore the set of non-singular matrices is not closed under addition, and therefore that it is not a vector space. Next, to show that the set of singular 2 by 2 matrices is not a vector space again. So let me consider again two singular matrices. The form A is equal to 1 1 0 1 and identity matrix 1 0 0 1. Let me find the vector addition. Here I will add the vectors A plus minus 1 times I. Their addition gives a new matrix 0 1 0 0, so which is a non-singular matrix. So therefore the set of singular 2 cross 2 matrices is not a vector space. So vector addition fails here. So sum of two singular matrices gives a non-singular matrix. Therefore it is not a vector space. So this is a very simple example. We'll continue with the problems after the following theorems. So we have two important theorems of the subspace. Number one is the intersection of any two subspaces of a vector space V over a field F is also a subspace of V. What this theorem says? The intersection of any two subspaces of a vector space V over a field F is also a subspace of V. So let us prove this theorem. The intersection of any two subspaces of a vector space V over a field F is also a subspace of V. That is, S intersection T belongs to V. So let us consider two subspaces of V, let S and T, over the field F. So now let me define their intersection. Their intersection will be a set of all elements, say alpha, such that alpha belongs to S and alpha belongs to T. This is how the intersection of two subspaces, the intersection of two sets will look like, right? So S intersection T is in the form alpha, set of all alpha such that alpha belongs to S and alpha belongs to T. So just we have to verify the vector addition and scalar multiplication. So here it is enough to take the condition of the corollary, the C1 alpha plus C2 beta. So to prove this belongs to this addition, C1 alpha plus C2 beta belongs to S intersection T. So now what I will do is I will take the two elements in the intersection, say alpha beta belongs to S intersection T. What this implies? This means alpha beta will be in S and alpha beta will be in T. Right. Any elements is in their intersection means it will be common to both the sets, right? So alpha beta belongs to S intersection T. We mean alpha beta will be in S and alpha beta will be in T. That's what I have written over here. Then, so directly for C1 C2 belongs to F, I will take their sum with respect to the scalar multiplication. C1 alpha plus C2 beta belongs to S and C1 alpha plus C2 beta belongs to T for all C1 C2 belongs to F. If this element in S and if this element in T, together we can write it as C1 alpha plus C2 beta belongs to their intersection. So therefore, according to the corollary, if any element in the form C1 alpha plus C2 beta belongs to S intersection T, we can say this set is this subset or set is a subspace of that we mean S intersection T is a subspace of V. That means the intersection of any two subspaces is a subspace of. And also we have one more theorem with respect to the union. What this theorem says: the union of two subspaces of a vector space V need not be a subspace. I'll prove this theorem by taking a suitable example. Let me consider two sets S and T in the form A0 such that A belongs to R, and the set T, set of all elements in the form 0B such that B belongs to R. So what will be their union? S union T, let me denote it by W, set of all elements such that alpha belongs to S or alpha belongs to T. Now I will take two elements in W. Okay, so the elements of S in the form A0 and the elements of T will be in the form 0, B. So their union is in the form alpha. So I am considering the two elements in their union, say alpha 1 and alpha 2. Alpha 1 is in the form 1, 0 and alpha 2 in the form 0, 1 belongs to W. What will be their sum? Summing up these two elements gives 1 plus 0 plus 0 plus 1, or we can say the vector addition. Okay, so vector addition gives 1, 1, which does not belongs to W in turn, which will not be in S or T. So therefore W is not closed under vector addition and it is not a subspace of R2. So we have some condition on union to be a subspace. So what will be that condition? If S is contained in T or T is contained in S, then union of S and T is S or union of S and T is T, then S or union T is a subspace of it. So upon this condition, if S is contained in T and T is contained in S, then the union of two subspaces will be a subspace of it. Otherwise it is not a subspace. Let's continue the problems. Show that the subset W set of all x1, x2, x3 such that their sum is 0 of the vector space V3R is a subspace of V3R. What is a vector space here? Set of all triplets, that is R3. We have to show that V is a subspace of R3. Sorry, W is a subspace of R3. That R3 can be written as V3R. So how the W is defined? For all ordered triplets x1, x2, x3 such that x1 plus x2 plus x3 is equal to 0. So as usual way, let me consider two elements of W in the form x1, x2, x3 and beta y1, y2, y3. Alpha and beta are the elements of W. Okay, so that their sum is 0. Okay, how the set is defined? In the same way, we have to consider the elements. Now let me have the condition according to the corollary, that is the vector addition and scalar multiplication in the form C1 alpha plus C2 beta. That is C1 times substituting for alpha x1, x2, x3 plus C2 times substituting for beta y1, y2, y3. See how here the multiplication, scalar multiplication and component wise addition will take place. Okay, stepwise we have to do the simplification here. Now multiplying C1 to each element and multiplying C2 to each element of beta, we get C1x1, C2, C1x2, C1x3 plus C2y1, C2y2, C2y3. Next component wise addition. This is according to addition of two vectors. C1x1 plus C2y1, C1x2 plus C2y2, C1x3 plus C2y3. So to show that this quantity belongs to W, we have to show the sum of components of the C1 alpha plus C2 beta is 0 according to given W, right? So W is defined as for ordered triplets such that x1 plus x2 plus x3 is equal to 0. Now we have just found the sum C1 alpha plus C2 beta. Now let us show the sum of these components is 0. So let me consider the sum. Okay, that is C1 x1 plus C2 y1 plus C1 x2 plus C2 y2 plus C1 x3 plus C2 y3. Here I'll use simple algebra. I'll just group the like terms. Grouping all the like terms, we get C1 times x1 plus x2 plus x3 plus C2 times y1 plus y2 plus y3. So as we know, sum of the vectors is 0 plus C2 times 0, hence 0. So therefore, by 1, C1 alpha plus C2 beta is 0. Therefore, the C1 alpha C2 beta belongs to W. Hence, W is a subspace of V3R. Next problem. If the subspace W is equal to x1, x2, x3 such that x1 square plus x2 square plus x3 square less than or equal to 0 of V3R is a subspace of V3R. So we have to show W, the set, is a subspace of R3. Okay. Next we have to verify the vector addition and scalar multiplication. Okay. So let us consider the two elements of W such that the sum of the squares is less than or equal to 0. Okay. Here I will consider the vector standard vectors in the form alpha is equal to 1 0 0 and beta is equal to 0 1 0, which belongs to W. So what is their sum? Sum gives 1 0 0. If alpha beta belongs to W, we can say W is a subspace. What happens to the sum? Sum is 1 0 0. Whether this vector will satisfy this condition or not. So squaring and summing up this order triplets, which gives 1 square plus 1 square plus 0, which is not less than or equal to 0. It's not less than or equal to 0, right? Because 1 square plus 1 square is 2, which is greater than 0. So this is not less than, not less than. This is not less than or equal to 0, right? This 1 square plus 1 square. So the vector addition alpha plus beta 1 comma 0, 1 comma 1 comma 0 is not satisfying the condition of the given set. Okay. So therefore, because 1 square plus 1 square is 2, which is greater than 0. Hence alpha plus beta does not belong to W. Therefore W is not a subspace of V3R or R3. Similarly, I have few more examples on vector space. Just have to verify the 8 axioms, that is closure law, associative law, distributive law, existence of identity and inverse with respect to addition and scalar multiplication. We should go through these examples. 5 and 6 are simple examples.